Welcome back. In this lecture, we will provide an approach to an analytical formula for the half-life in beta decay via the Fermi theory of beta decay. In the last couple of lectures, we had looked at this formula. So here, P indicates the momentum of the beta particle that is emitted in a beta decay. And the main issue that is sort of different from alpha decay is that the energy spectra of beta emission is a continuous spectra. For this, we needed a model that is different from the models we had looked at in the past. So that provided the context for the Fermi theory. We have explained the meaning of this expression, at least qualitatively, you should be able to understand all these terms, even if you cannot go through all the mathematical details. The important factor is the statistical factor. This provided the explanation to rationalize the parabolic dependence of number of particle versus energy. So this term is the most important factor which rationalize experimental observation. Here, W and eta are dimensionless quantities, which we have defined in the previous lectures. Overall, what is that we get from this theory? Here, this denotes the probability of finding a beta particle at a particular energy W. W is a dimensionless energy. This is the width or the window within which we are looking at the probability of finding a beta particle. And this is the left-hand side. On the right-hand side, we have all these quantities. We have derived, we have looked at these expressions in a qualitative manner. This is the Fermi factor, which we looked at in the lecture on Coulomb interaction in beta decay. And this is the transition matrix and so on. So if you want to connect this to the experiment, the connection is made via this expression. So this is an expression which has been derived in the past. This is the half-life of in beta decay. This is the decay constant. So here we are integrating from between two limits. The limit wherein when there is a radioactive beta decay, the beta particle gets no energy. That is, all the energy, let's say, goes into neutrino, and all the in the other limit, all the energy that is released goes into the beta particle. So if you remember the energy conservation equation, the energy can be distributed between two particles, the beta particle and the antineutrino. So if you go and look at that expression and non-dimensionalize that in terms of W, you will get the meaning for these limits. So that can further be written in this manner. Okay, so you have to connect the previous slide, the last expression from the previous slide, to this expression. So here we have collected all the fundamental constants into 1 by T naught. So this is all just a constant. So what we have is this expression. So this is expressed in a particular manner in this community. So what is done is that this times this. Okay, so that is this expression. This times this is equal to ln 2, that is 0.693 times T naught divided by this quantity. So this expression comes from this expression. So why do we write it in this manner? So what we have here is this is a constant. This is all the expression is provided here. So ft, which amounts to these two terms, is an universal constant divided by this quantity. So to simplify further, to get some analytical expression, we need to have an analytical expression for this quantity. This can be done under certain limits. Okay, so this involves some more involved quantum mechanics. We won't look at these approximations, how to get a simple expression for this quantity, but it can be done. It is presented in some more detailed literature in nuclear physics. So using such approximation to get an expression for this, we can get an expression for log of f. Okay, so remember what is the significance of f. Okay, so f is indicative of decay constants. So log f under certain limits can be obtained for beta minus decay, beta plus decay, and for electron capture. These are the three different beta decay mechanism, and it is possible to get an expression for log f using certain approximations for transition matrix, and these expressions are widely used in beta decay. So even though these are approximate solutions for log f, they are fairly powerful, and they give you a general feel for on what parameters that does f depend on. So the main thing is it is proportional to log E naught, which makes sense. But these expressions are rather hard to rationalize in a qualitative manner, but we will just use these expressions, and at least it gives you an idea on what factors does log f depend on. In the next lecture, we will give a preamble to selection rules in beta decay. So the objective here is to get some broad issues connected to quantum mechanics without going into a lot of details, give you a physical picture on the basis of selection rules in the context of beta decay. And the principles are actually rather applicable to a variety of selection rules in spectroscopy and so on. That will be taken up in the next lecture. Thank you.